So today we're going to talk quickly about how to matrix exponentiate diagonal and diagonalizable matrices. So I'm just going to do this by a quick example. For the diagonal case, it's pretty chill. So my goal here is to calculate e to the 2001t. Okay, so what I'm going to do is I'm going to think, okay, what are powers of this matrix, right? So I'm looking at this matrix and I'm thinking, okay, so A is 2001. A squared is going to be, well, it's 2001 times, the heck? My pen back thing. Times 2001. Right, so I'm going to pick this up, I'm going to drop it on, I'm going to multiply. Out of this, what I'm going to end up with is that I'm going to end up with 2 squared, 001 squared. Okay. If I do a cubed, I'm going to end up with 2 cubed, 0, and 1 cubed. This is kind of a cool fact that essentially a to the n for a diagonal matrix is going to be whatever the diagonal entries are to the nth power. Oops, that's not a 2. That's going to be a 1. Okay, so that gives me a formula that I can write out. So I'm like, okay, so I'm going to write this out using power series. It's the identity matrix, right, plus A, so 2001 times T, plus 2 squared 001 squared times t squared over 2 factorial plus 2 cubed and 1 cubed in the diagonal and t cubed over 3 factorial here. And then I'm going to get a bunch more of these. Now, the cool thing is here I can just do that scalar multiplication in, and then I can add these up, and I can see that in this top right corner, oops, we're going to have to make this puppy pretty big. So in this top right corner, well, sorry, let's do the easy ones first. In the bottom left corner, I've got a 0. In the top right corner, I've got a 0. Now, right here in this top left entry, I've got 1 plus 2t plus 2 squared t squared over 2 factorial. Resist the urge to cancel 2's there. Plus 2 cubed t cubed over 3 factorial. And so on. And then in this bottom corner, I have the exact same thing. This is one of those moments like where, thankfully, we're working on a computer and we can just copy and paste some crap. Okay. Then you might notice this stuff here is actually just, oops, I lied. I can't just copy and paste that. These need to be 1's. Okay. The nice thing I can do here is I can notice that this stuff here is exactly what I would get out of the power series of e. So that's e to the 2t there. I've got a 0, I've got a 0. And down here I have an e to the t. That's cool. That means that if I have a diagonal matrix, I can just exponentiate the diagonal and I don't need to worry about this whole power series thing very much. That's a really neat trick. So I think that's maybe a start. Let's go look at a slightly more complicated case. So here's my slightly more complicated case. Remember when I talked about diagonalizing matrices a couple of days ago? What that means is that I could write A. So let's say A is diagonalizable. Diagonalizable. I can't spell, sorry. So A is diagonalizable means that I can write A as some matrix X, some lambda, some X inverse. and I'm calling back a bit. So the thing I'm calling back to is right here. So I'm using this formulation that we got from eigenvalues and vectors, right? When we talked about eigenpairs, this was a formulation we got. So the reason I'm talking about this now is I'm trying to make powers of a matrix, right? So I'm trying to write down e to the at. And the way I'm going to write that down is I'm going to say, okay, that's the identity matrix plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial plus yada yada, right? And then here's what I'm going to do. I'm going to sub this guy in for my a's. So I'm going to say that's I plus x lambda x inverse t plus x lambda x inverse, that's 1a, x lambda x inverse, that's my second a. So this whole thing here is a squared. And then I've got a t squared over 2 factorial. And then I've got, yeah, I've got an x lambda x inverse, x lambda x inverse, x lambda x inverse times t cubed over 3 factorial. And you can see how this is going to go. These are going to get a little annoying to write down. The good news is the x and the x inverse cancel, the x and the x inverse cancel, the x and the x inverse cancel. And so I can pretty quickly write this thing down as I've got the identity matrix plus x lambda, and I'm going to do a little factoring here. I'm going to bring this scalar t that could go anywhere in these symbols. I'm just going to bring it next to the lambda. Right, it's just a scalar so it can go any place. Here I'm going to have an x. I'm going to have a lambda squared. I'm going to have a t squared over 2 factorial here. And then I'm going to have an x inverse. And then my next one, I'm going to have an x. I'm going to have a lambda cubed. I'm going to have a t cubed over 3 factorial. And I'm going to have an x inverse. And so on, right? So everyone's going to be led fore and aft by an x and an x inverse. Now, this identity feels like I ought to be able to do some factoring here, but I can't factor anything out of the identity. So I'm going to rewrite the identity matrix as x times x inverse. And then out of the left-hand side of this power series, I'm going to factor in x. And out of the right-hand side of the power series, I'm going to factor in x inverse. And then what's left? Well, the first term, I've got an identity matrix. The second term, I've got a lambda t. The third term, I've got a lambda squared t squared over 2 factorial. The third term, I've got a lambda cubed t cubed over 3 factorial. And so on. Notice that what's in here is just the power series for e to the lambda t. So this makes my life way easier. If I have a diagonal matrix e to the at, I can always write that exponential as x times e to the lambda t, and I know what e to the lambda t is going to look like. Right? I just did that with a diagonal matrix up here. And so if I've got my capital lambda, right, is just down the diagonal my eigenvalues, I'm going to have x, and then I'm going to have here a matrix that's going to look like e to the lambda 1t, e to the lambda 2t, and so on until we get to e to the lambda nt. Big fat zeros top and bottom, and then I'm going to have my x inverse. Remember, though, that I have to be able to find linearly enough, right? I need to be able to find n linearly independent eigenvectors to make this diagonalization work. Doesn't always work. It's an if, right? So if A is diagonalizable, then we can write it this way. Then we can exponentiate relatively easily. Cool? All right. I think that's what I want to say for this. Thanks for watching. We should do an example. Let's do an example quick. So I'm going to do an example with this guy, right? So I'm just going to grab my example here and I'm going to go down and I'm going to say, all right, let's do an example. Let's calculate e to the at for a is something, and we'll recall this thing that I copied. Okay, so the matrix that I'm calculating my exponential for is 3214, right? So that's, all right, I'm going to have e to the 3214t is going to equal, and from what I just did, right, I'm going to get that matrix X. So this guy is written backwards, right? But I just need the X and the lambda matrix out of it. So I'm going to get my X. That's 1, -2, 1, 1. And remember, this is the first eigenvalue and the first eigenvector, second eigenvector. That's in the columns, right? And then I'm going to have e to the 5t, 0, 0, e to the 2t. And then I'm going to have this multiplied by the inverse, right? And that's it. So this is this is done, right? I could fiddle this around a little bit. I could actually calculate this inverse and do some multiplication. But frankly, I'm real happy with this. That's done. It's as easy as that. Where did I get these things? Well, I needed to solve for the eigenvalues and then find the eigenvectors. So there's some work there. But once we've done that work, we kind of get the exponential for free, which means that I can solve a differential equation using this thing, which is hella cool. Thanks, guys. Catch you on the next one.